Well, good morning, everyone. Welcome to EECS 151, 251A, our last lecture together. I was assuming we were going to have a packed house today, but expectations have been defied so far. We'll see who trickles in. So I'm going to be giving the first half of today's lecture to finish our conversation about SRAM that we started on Tuesday. And then Professor Shao will conclude with some general thoughts about the course and possible next steps for you all. So let's get started with this warm-up based on the content on Tuesday. Go ahead and try this on your own for a few minutes. Okay, give me a quick thumbs up if you're ready to talk about this one, or just keep looking at your paper if you need another minute. All right, let's take one more minute for folks to think about this. All right, let's discuss this one. I see some folks are still pondering. and that is totally fine. This is our classic 6 transistor, 6T SRAM bit cell that we went over on Tuesday. And we're trying to perform a write operation. So in this write operation, with in particular Q set to 1, and we're trying to write a 0, we've set the bit line to 0. So which are the 2 devices that are important for this analysis? Any thoughts? Which transistors are on based on this initial configuration? Say again? Yeah, M2 is on. What else? M3, yes, because it's being driven by 1. Okay, and then once the word line goes high, what else is on? Right, exactly. So these devices are on. Now, which ones do we care about? Well, remember that the access transistor is only good at pulling down, right? So on the right side, M6 is trying to pull up, but it's pretty bad at it because it's an NMOS. So the real action, the real fight is happening between M5, which I'll kind of double circle, and M2. So whenever I'll always think about for write, which bit line is 0, that's the side that you need to be thinking about for the analysis. So that's where the access transistor is pulling down. Okay, so those transistors are both on, so we can use our simple resistor plus switch model to try and analyze what's going on here, right? We have VDD, then we have the M2 resistance. And then we have the M5 resistance. I guess I notated them as R on M2 and R on M5 above. And then the bit line is grounded, right? And here is our node Q, which is what we need to analyze. Okay, and then so we know initially Q, we can start to draw this waveform. Q is VDD, right? Q is 1. What is the steady state value of Q after the word line turns on and the switch for M2 is closed? What happens when you resolve the resistive divider based on the resistances that were given here? Thoughts? Yeah. Right, which is?
Oh, wait, that was the numbers. Two-thirds VDD.
Right. So the steady state is that Q gets pulled down only to 2/3 VDD. So something's off here. Has this cell actually been written by this write? No, we didn't. We never flipped the value, right? If we look at Q bar, right, you can think of 2/3 of VDD as the input to the opposite inverter, which means that Q bar, which starts as 0, is only going to nudge up a very tiny amount, right? Because the slope of that transfer curve of the inverter is greater than 1. So it's reinforcing its initial value because we haven't flipped over the crossover point. Right, the voltage needs to drop past VDD over 2 in order for the access transistor to win the fight and flip the bit cell. So this is a very poorly designed SRAM bit cell, right? Because in particular, for the case of the write, we always need to have the access transistor M5 stronger than the pull-up transistor M2. We talked about that writability constraint last time. And so this is an example of a write failure, where the access transistor was not strong enough to complete the write. The resistance was too high. So hopefully this gives a little bit of intuition about why we gave those inequalities last time about, M5 must be stronger than M2. M1 must be stronger than M5 for read. Yeah. Correct. Yeah. Stronger always means more current, means less resistance. Yeah. So you always have to perform that mental flip in your head when you're thinking about it. Stronger also means wider, right? Because wider transistor width or larger transistor means more current, lower resistance. Okay, any other questions about the warm-up? So we're going to talk about one more thing with bit cells, slightly unorthodox, but I was thinking about my explanation of how you read a bit cell last time, and I realized that I did not do a good job explaining it too well. So I'm going to try again a little more carefully. Okay, on the warm-up, we talked about writes. Now we're going to go over again how the read of the bit cell works. So let me be as clear as possible about what the step-by-step is here. So step one, when we want to do a read, is we're going to pre-charge both bit line and bit line bar, so both sides, to VDD. So they're both set to 1. Step 2 is that we disconnect the bit lines from any driver, from any transistor that's forcing them to a value. And we leave them in this floating state. Okay, they're still equal to 1, right? They still have all that charge stored on these large capacitors. Remember, these are very long wires with lots of transistor sources hanging off of them, right? So these are big, big capacitors full of charge, but nothing's driving them, right? Nothing's connecting them to VDD anymore. They're floating at this point. And then step 3, we assert the word line. We turn on the word line. We turn on the access transistors. So let's think about what that does with this circuit, right? So in this example, we have Q equal to 0, but the bit line is equal to 1 on the left side. And on the right side, the bit line is 1, the storage node is 1, so nothing's happening, right? Bit line bar is just staying at 1. So again, the left side is the important one for this example. So we start with Q at 0, and it's being pulled down by this inverter, by the pull down device in this inverter, which, using the notation from the transistor diagram, we call that M1, right? So this inverter is pulling down node Q, which is here. And then the access transistor is pulling up based on this bit line, right? But the bit line isn't connected to VDD anymore. It's just a big capacitor. So this is the bit line. So this is the key subtlety about the read operation, is that there's a short-term and a long-term behavior, right? In the short term, this capacitor of the bit line is so big that it's effectively equivalent to a supply voltage, to a VDD. There's so much charge sitting on there that in the very short time scale, it's like this. And you get a resistive divider, you get a fight between M5 and M1. And you can see that in the waveform where Q in the short term is settling at this divided value, right? It's some ratio between 0 and VDD because the transistor M1 in the inverter is pulling down, but the access transistor is pulling up. So they're fighting. In the long term, the bit line starts to actually discharge, right? So in the long term, this behaves not like a resistive divider, but like an RC circuit, which discharges exponentially over time. And so as that capacitor discharges, eventually the bit line, this tiny, tiny access transistor is working really, really hard to pull that bit line down, to discharge it to ground through the access transistor. And so slowly, 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 the bit line discharges. And then eventually, once all that charge is gone, then Q will settle back down to 0 because you're dividing between 0 on the top and 0 on the bottom. So this is the key distinction I want to draw when thinking about the read operation, is that in the short term, it behaves like a resistive divider, and a long term, it behaves like a discharging RC circuit. And you need to make sure that M1 is stronger than the access transistor so that Q doesn't flip its value accidentally, right? If this value Q gets too high, then it'll accidentally flip the value when we're trying to read it, which is not what we want. Okay, yeah, questions?
It lines to like 2/3 of VDD or something, so that it's more likely to lose the fight.
You can do that. Some SRAMs do that, actually. We're going to talk a little later about how we read the bit lines also. It turns out that we don't need to wait until the bit line has all the way gone to 0 before we read the value out. But stay tuned for a few minutes for that. Yes. Right, so here's Q. This is a read operation. So we want to maintain the value of the cell, right? So we want Q to stay as a logical 0 and Q bar to stay as a logical 1. If Q goes too high, right, then eventually you'll be passing a 1 into this inverter instead of a 0. And then that would force the value to flip, which is great if you're trying to do it right, but we're not trying to write here. Like one of the key features of SRAM is that the reads need to be non-destructive. So if that happened, that would be called a read upset, which meant you're trying to read the cell, but you accidentally flip the bit. Yes, that's 2 slides from now. Yeah. Okay, so hopefully this is a little clearer about how the read operation works. Sorry for muddling the explanation last time. Are there any other clarifying questions about how the bit cell works? Because after this, we're going to zoom out and talk about other components of the array. Okay, can folks show me a quick fist of 5? How are you feeling about understanding the SRAM bit cell? Yeah, looks like average is about a 3, which is about right. This is, as I said last time, I think this is the most complicated circuit that you have to wrap your head around in this course. So don't feel bad if it doesn't click right away. Hopefully you've been getting some more practice on your homework. I encourage you to attend discussion this week if you haven't yet. Yeah, it'll click, and it's a very cool circuit once you do kind of disentangle how it actually works. For today, we're gonna move on and finish talking about the SRAM periphery. So recall that the SRAM is made up of two parts. There's the array, which is just lots of bit cells in a rectangle. And then there's the periphery, which is the stuff around the edges. So last time we talked about the row circuitry, the row decoder, which takes the address bits and figures out how to turn on exactly one word line at a time. Today, we're going to talk about the column circuitry. That sort of has three parts. One is the bit line conditioning, which is the thing that sets the bit lines to one, pre-charges the bit lines to one, like we just saw in the read example. And then the second part, so bit line conditioning in this diagram, it's drawn up at the top, although it's not necessarily living at the top in an actual layout. It might live at the top or the bottom. And then we have some more circuitry down here to either do a read or do a write. And so we're going to talk about those three components and how they work. So bit-line conditioning is actually quite simple. Here's an example on this slide, shows a bit-line conditioning circuit. We're going to take advantage of the fact here that the clock has a positive half and a negative half, a positive phase and a negative phase. The clock is denoted with the Greek letter phi in the circuit example here. And so you notice that when phi is high, then phi bar is low, and that's going to turn on these PMOS, right? So we'll assume that bit and bit bar have an unknown value at the start. You'll sometimes see these sort of X's drawn in the waveform to say that the value is unknown and may be transitioning during that period. But then as soon as clock goes high, it's going to pre-charge, set high, these bit lines. And then when the clock goes low, these PMOS drivers are turned off, and so the bit lines are no longer being driven by this circuit, right? They're floating. And so again, we might have transitions going on, which I'll represent with these X's. And then at the next clock edge, we recharge again. Right. So this is bit line conditioning or bit line pre-charge. It's a very simple circuit, and its only job is to make sure that when the clock is high, the bit lines both go to 1. Not too bad so far. The next one's a little trickier. After the pre-charge, we need to figure out what we're doing in when the clock is low. And when the clock is low, we're either doing a read or a write operation. So first, let's talk about the write operation. Now, you can see an example of the write driver circuit in the top right. It's just made out of, an NMOS controlling these bit lines, bit and bit bar, and then a small amount of CMOS logic to determine, well, are we doing a write? If so, are we writing a 0 or 1, which is the data bit? And then what's the clock? Right, so we know from the previous, let's assume, just for the sake of generality, that the bit lines start low. It doesn't really matter. We know from the conditioning circuit that they'll be pre-charged high when the clock is high. So then we need to figure out what they're doing when the clock is low. Well, we're told that write is high and data is high. So if you work out the logic in this pre-inverted AND gate, if you want to call it that, or inverters plus AND gate, you'll find that write Q1 is low in this example. Write 0 Q1 is low and write 1 Q1 is high. Okay, so we set this to 0 and this to 1. So then if we think about what that does, if write 1 Q1 is high, then when the clock toggles, right, when the clock is high, that's not doing anything. But when the clock goes low, it's going to finally turn on this gate. So yeah, sorry, let me correct the notation there, or correct the waveforms. I can find the eraser. No, it won't let me bring up the eraser for some reason. So I'm going to do the ugly thing and kind of scribble this out. Right. So these both start low. These both start low because when the clock is high, then it's inverted and goes through the AND gate. Right, 0 Q1 stays low. Right, 1 Q1 starts low and then goes high when the clock is low. And so when write 1 Q1 goes high, that's going to turn on the NMOS and that's going to pull bit bar down. And so we have bit high and bit bar low. And if you think back to our write analysis, when we were writing a bit cell, that's exactly what we needed to set to write a 1 into the bit cell. And then at the next pre-charge, these are going to both go high again. Okay. Yeah, sorry for the scribbles. Any questions about what's going on here?
This is the condition we have.
Yeah, these are right. Those are going to start, or we can assume that they're low or that they're off to start. And in particular, they're always being driven to 0 when the clock is high, right? Because we have these clock inputs to the AND gate. So during this first phase, we call this the pre-charge phase because the bit lines are just getting pre-charged from the circuit on the previous slide. And then this phase, we're doing the actual write by driving one of the bit lines low and the other bit line high. Which you'll recall, if we zoom into the individual bit cell, is how we write the cell by yanking one side down. And then the access transistor overpowers the feedback and writes that value into the cell. Yes. Correct. Yeah. Sorry. Yeah, I really gotta find why PowerPoint's not giving me that eraser. This is very obnoxious. Yeah, here we go. Okay, I'm going to redraw these or erase the scribbles so it's clear what's going on. Okay, so these are more accurate waveforms, right? 0 Q1 stays low always in this example because data is 1. Whereas right 1 Q1, when the clock goes low, it goes high, which causes the bit line to discharge. And we said previously that these bit lines are these big, huge capacitances, right? There's lots of capacitance. And so in practice, you have to have really big driver circuits, really big buffers on the output of these AND gates in order to pull the bit lines down quickly. Unlike the dinky little access transistors inside the bit cell, which are pulling them down very, very slowly, this needs to pull it down very quickly so the write can take place. So you need to have big, big drivers. Yeah.
Why not also include other bit line up? Like it's already pre-charged, but isn't it gonna sag as we?
Yeah, you're right. You could and some SRAMs do continue to drive the other bit line to 1. We're showing a simpler version of the right driver circuitry here that saves some area, but may impact the writability slightly. In practice, it doesn't matter that much because the side that's 1, as we know, the access transistor really is just not going to do that much, right? So it's contributing so little to the actual writing of the cell that we typically just ignore it in the analysis. But it's a good question. Yes.
What?
Yeah, we were doing that just in this example. I guess that's probably not that realistic because typically in a previous cycle, one would always be higher, one would always be low. So maybe I'll draw it with the x's here to show that it could be in any state coming into this example. We don't know. Okay, these are all good questions. So that's the right driver. Let's talk about how we do a read. And for read, we're going to connect a different set of bit lines or a different set of circuits to the bit line, which is the bit line sensing circuitry. The goal of the sensing circuitry is to read small differences between bit and bit bar, right? We haven't talked about this much, but in addition to readability and write stability, writability and read stability. We also care about, the traditional digital design optimization goals, notably performance, right? So if you make all these transistors in the bit cell as small as possible, then they're going to be really slow at everything they do. And in particular, the access transistors, if they're pretty small, are going to be really slow at winning the fight and pulling down that bit line voltage. And so typically, we don't actually let the bit line voltage go to full swing, full rail, before we decide what the value is, before we perform the read. Instead, we add this sense amplifier circuit. If you have or are taking 140, you are probably more familiar with this, but this is typically implemented as an analog circuit that is going to magnify small differences between bit and bit bar voltage. So let's look at an example of the waveforms for this. So again, we don't care what these values are beforehand, but we know that during pre-charge, bit and bit bar are both going to go high. Okay, and if bit and bit bar are equal, well, I guess we don't know what the output is on the previous cycle, but if bit and bit bar are equal, then the output is actually going to start at VDD over 2, right? It's right in the middle. The sense amplifier has nothing to amplify in either direction yet. But then we know that during the read operation, one of these bit lines, let's assume in this case that it's bit, so we're reading a 0, is going to be pulled down very slowly. Right? It's not even pulled all the way to ground by the end of the cycle, but it's pulled very slowly. And so there starts to be this tiny difference between bit and bit bar. And a good sense amplifier will very quickly detect that difference. Even this tiny difference here, where bit bar is still at VDD and bit is at VDD minus epsilon, some very small value. A good sense amplifier will detect that and amplify it. And it'll figure out, okay, let's drive that voltage to ground immediately and perform that read. And then in the next cycle, the bit lines get pre-charged again, and we start again. Yes?
So why is output low?
You can implement it either way. Yeah, it depends on the op-amp implementation. If you're using VDD over 2 as a reference, for example, so you'll have equal rise and fall times. That's a common choice, but you don't have to do it that way. Yeah, the important thing is just that it can sense small differences and immediately push it to one rail or the other. Yeah.
Which,
So which signal are you asking about? So when the clock goes low, the bit line very slowly starts to drop, right? We saw in the read operation, it's very slowly just the access transistor of a single bit cell in that whole column of hundreds of bit cells is very slowly discharging that bit line, right? But so this waveform decreases very slowly, but the sense amplifier can amplify the small difference between bit and bit bar and much more quickly detect whether the output should be high or low. Yeah. So in particular, this transition is going to happen as soon as you trips the whatever threshold specification the sense amplifier is designed to. Maybe if the sense amp can detect a difference of 10 millivolts or 20 millivolts, whatever it might be. So that's the circuitry in the bit line to perform the read. And you'll notice that we have three different things each hanging off of all the bit lines, right? We have the pre-charge circuit, the write circuit, and the read circuit. And so they all need to kind of coexist in parallel, which makes for an interesting layout challenge because they all need to be pitch matched into the columns of the array. But this is doable. People do it. People build these SRAMs. Okay, any last questions about the column circuitry, any of the pieces that we talked about? All right. Let's do a little brain teaser here with the poll everywhere. Please go ahead and give this one a try.
yeah. Okay, so yeah, that would be, it would be, it's like it's so hard as well as these pieces. Read the this.
Okay, I see responses starting to come in. Let's take another minute for folks to think about this one. Please respond in the poll if you haven't already. Okay, interesting. So we have a little bit of differing opinions here. So I'm going to turn off the poll. Please go ahead and turn to your neighbor and try to convince them that you are right and they are wrong. Go ahead and take a couple minutes.
It's in the existence, was sustainable types of thing. Oh, right. It's the code that it's It's in that case.
All right. So who's who has successfully, did anyone successfully convince your neighbor? People are guessing a little bit. Okay, let's talk about it. So if we are setting the word line to a lower VDD, so which transistors is that affecting? Pull up, pull down, or access? Right. So this is affecting the access transistors. And we're decreasing the gate voltage, the VGS. So is that making them stronger or weaker? The access transistors are getting weaker, exactly. Okay. So now we need to just think about what's fighting what in each case, right? So what's going on for right with those access transistors? Is this helping or hurting right?
The high bit line in writing is almost no impact. So this should have very little impact on it, or yeah, I think.
Well, but both access transistors are being used, right? Are getting the same 0.8 VDD. Thoughts?
For the sake of viability, we want M5 to be stronger than M2.
Yeah.
So we want the access to be stronger than the pull up, right? But if we weaken M5 with decreasing viability, that ratio is worse.
Yeah. So our weaker access transistors it makes, for right, you're exactly correct. You need a strong access transistor for right, because you need to overpower that PMOS, that M2. So it's going to hurt writability. Yeah, you're correct that the hurt is mainly coming on only one side, like we talked about. But it's always going to be one of the sides needs to be writing. And so that side is going to be penalized by this. Okay, what about read? Someone else? Do we want strong or weak access transistors for read? Yes.
You don't want it to this, like, you don't want the RC stuff to happen, like,
So if you have a strong access transistor, then that'll okay, bigger resistance, which is weaker. Yeah, okay. So you want a weaker access transistor for read. And so therefore this is going to help read stability. Does that make sense? Now, unfortunately, it's also going to make our read slower, right? Because it takes longer to discharge that capacitor, as you're saying. So for that reason, this is not a common technique to improve read stability in SRAMs, because we care about both speed and stability. But we want those access transistors to lose the fight against the pull down and not upset the node. Okay, question in the back? Yeah, so think back to our transistor models, right? We have these different curves, these different VGS curves. So if VGS is lower, then our saturation current is lower, and so that's equivalent to a higher resistance. Cool. Okay, so I think, let's see if I can do this. Yeah, I think we had a plurality of correct responses, but some folks flipped it around. You know, some folks inverted it in their heads, I think. So as we said, the correct answer here is C, decreased writability, but increased read stability. Yeah. Yeah, so it hurts writability because for a write, we want the access transistor to be strong so that it can overpower the feedback in the node. Right? For a write, we want this access transistor to win the fight against the pull-up. But for a read, we want this access transistor to lose the fight against the pull-down. So anytime you mess with the access transistor, you're always going to be helping one way and hurting the other way. Okay, I'm definitely sensing that people still are feeling a little uncertain about SRAMs. We'll take one more question.
So are viability and read stability always like data?
Not always. There are techniques that you can use to improve one while not harming the other. But that's more of a 251 or 241B topic to talk about those kinds of advanced SRAM designs. Okay, I do want to move on because I want to make sure that Professor Shao has enough time to talk about the conclusion to the course. So we're going to move on from SRAMs for today. Briefly to summarize, SRAMs are highly optimized, as we talked about, to maximize storage per millimeter squared. It's all an area efficiency play. That's the whole reason to use SRAMs. Oops, I think I skipped or deleted a slide somewhere. And it is an important slide, so I'm going to go find it. Yeah, this one. Cool. It just like disappears. Okay, you can see it here briefly. So I do want to talk a little bit about the sort of practitioner's perspective about SRAM, because this is also important to understand. So these SRAM layouts, you can see an example of a bit cell layout in the top right corner of this slide, are super, super highly optimized. The transistors are squeezed in as tightly as possible. In fact, the foundries define what are called these special push rules, special DRC rules that you're only allowed to use inside the SRAM bit cell. So if you tried to put transistors this close together in a standard cell, in an inverter, a NAND gate, you would get a DRC violation. You couldn't tape it out. The foundry wouldn't let you. But for SRAMs, they have these special rules that let you pack things in super tightly. We talked about how the periphery circuits need to be pitch matched to the bit cells. The periphery ends up typically being 30 to 50% of the area of a typical SRAM, so it's non-trivial. It's important to think about and optimize, but the bit cells are usually the majority. SRAM macros, right? These are the, what in the ASIC lab, what you're actually instantiating in your layout. typically you don't just have a few fixed sizes to choose from, because once you can generate a bit cell, you can kind of lay down an arbitrary number of them. And so in practice, we tend to use these SRAM compilers, where you say, you put as input to the compiler, please give me an SRAM that's 64 bits wide and 128 entries deep. And then the compiler will churn. It'll spit out a DRC clean layout, a schematic, all of the characterizations needed to use this cell in your design. Very large SRAMs, more than certainly anything in the megabit range would need to be composed out of multiple macros, because there are maximum sizes for these things. Finally, for small memories, SRAMs no longer are a win, because the overhead of the periphery circuitry outweighs the area savings of the bit cells compared to flip-flops. So for anything less than a kilobyte, typically, the transition point varies depending on process and technology and so forth. But for very small memories, just use flip-flops. It's not worth bothering with an SRAM. Finally, a note on process technology. It's very interesting to notice that SRAM bit cells have basically stopped getting smaller with recent process nodes. So a 5 nanometer bit cell is the same size as an 18 angstrom bit cell, or more or less. Maybe they've gotten very, very slightly smaller. This is because with everything else on the chip, they can play lots of tricks to kind of squeeze it down and down, but the SRAM cells are already so squeezed that there's no more tricks they can play. They basically run out of games. So these are the very, very smallest transistors that they can build. And for the last 5 years or so, they haven't gotten any smaller. And there's not obvious prospects for them to get much smaller in the future. The overall SRAM macro is still scaling because they can squeeze and play tricks with the periphery, but the bit cells themselves are stuck. Okay, I did want to mention this slightly more practical minded perspective. So any quick questions about this stuff? Yeah.
Why is there the max size that you talked about before? Like, why can't we just make the bigger?
Yeah, there's a few different reasons. One, you can think about, right? We said these the bit lines are these huge capacitances. So the more entries you add, the more capacitance you have on the bit line. Eventually, you have so much capacitance that a single bit cell can no longer discharge it within a meaningful cycle time. So there are other constraints. That's an example of one, where eventually things just get too big, and the careful design decisions made around these SRAMs no longer would work. Okay, I don't know why that slide. All right, PowerPoint is being grumpy. I'm gonna have a little restart. Let me just leave it in this view, and then we'll restart PowerPoint at the transition. So very briefly to summarize, SRAMs optimize area. They're an array of these bit cells. Each stores 1 bit. We need to carefully design the bit cells. We have row decoders along the rows and column circuitry along the columns that form the periphery. Okay. There's a lot of administrative stuff at the end. I'm going to just kind of gloss over it, and I encourage folks to read carefully on Ed if you have questions. So final project checkoffs have been announced next week, next Wednesday and Thursday. You need to sign up for a slot with your partner. There's a bunch of preparation that you need to do ahead of time. The design contest also will close next Thursday at 5 p.m. So you need to upload your stats to the leaderboard to enter the design contest if you haven't done that already. The final exam is the week after that, the Tuesday after that. It's in 2 different rooms. So you need to go look what your last name is and which room you need to go to. There will be a review session, not tomorrow, but a week from tomorrow, a sort of special one-off discussion. That's all final exam review content in Corey 540, the normal spot. And I will also have my regular office hours next Tuesday, if anyone would like to come and talk about anything in the course. Finally, we really want everyone to fill out the course evaluations because we want to know how we did and what we can do better in future. So please do this. The URL is here. You probably know it and have received emails about it in your Berkeley email. If we get 90% participation, everyone gets a little extra credit. So please fill out the course eval and encourage your peers to do so as well. Any very quick questions on administrative stuff? All right. Sorry to be in a rush here, but I don't want to. So let's see if this works. Yeah, seems not. All right. Well, I liked. Oh, where did they go? PowerPoint's so grumpy. Okay, I'm gonna quit out of PowerPoint and go back in. We'll show the cool little AND gates that people made in lab, and then we'll turn it over to Shop. Hmm? Okay, here they are.
Oh.
I don't know. If someone posted this on Ed, I thought it was really cute. So.
Gave that as a gift. My outfits.
Okay, so we'll take a 30-second break while we transition here. Sorry for running over.
Well, isn't Ben really great? Let's give Ben a round of applause for teaching this class. Amazing, amazing. Thank you so much, Ben. Okay, great. Good to see you all. How is everyone doing? Good? Surviving? Okay. We're going to transition to some lighter topic.
I think I turned the mic off.
Okay. I'm really, really happy we finally get Ben to actually teach the SRAM topic. Like when I reach out to Ben, like I really, really hope you to teach SRAM because Ben is like one of the SRAM experts and he actually have a lot of experience with different SRAM designs. So it's really good we get Ben to do this. And moving forward, as we are wrapping up the semester, it's hard to imagine it's already the end of the semester, right? I still remember like 3 months ago, we just get the course started. As we're wrapping up the semester, I'm going to talk a little bit more what's moving forward, right? What are different courses? And also want to leave you folks a little bit thoughts on what's going on with this technology, what's going on in the field, and how you can actually move forward from the course, especially how you can actually navigate your own engineering and research career. So let's get started. I guess we show this at the beginning of the semester, and when we talk about this is a class, and very importantly, about engineering, right? We mentioned in particular, we'll cover a lot of interesting concepts during the lecture, but one of the most important part is the labs, right? I hope you folks get to discover the labs, learning different tools, learning new languages, figuring out what you can do and also cannot do, and also getting a little bit better about all the different tools. But all of those are actually very important and useful experience for you to actually navigate your career moving forward. So I hope this is really fun. You get to actually do things and also complemented with a concept that we talk about in the lecture, help you to actually navigate different components. One thing, I still come back to these slides. You see, I guess, different version of the slides from different computer architecture classes. You may also see different components from the system class. One thing really important about the hardware design, purely because of the complexity of the hardware design, right? We actually want to navigate all the different layers. We set up all the different abstractions to think about what are the different layers, where we are. I like the way Ben actually structured the lecture. Well, there are so many different components, right? What kind of layer we're talking about and how we actually see all the different layers correlate and interact with each other. we'll talk a little bit more moving forward, right? But this is also a really important opportunities to think about when you actually get to your own hardware design. How do you define your own layer of abstractions and also be ambitious and also thinking about opportunities that you can actually across those layers. A lot of opportunities actually, especially we'll talk a little bit more with this kind of more vertically integrated hardware design, there are also even more opportunity to think about how you actually scale beyond those layers. But one thing, especially with the semiconductor industry, is that there exists a lot of really important tools and methodologies already, and we hope this course can give you at least a rough overview of different tools and the things that you can do with existing methodology. So when we actually think about the field, right, it's really funny when I try to actually put these slides together, I realized when I first maybe solo taught this class, when I mentioned exactly this slide as the field has advanced, that's the time when we actually get to the M1, the processor where Apple actually stopped using ARM, stopped using x86 and transitioned to ARM ISA, right? So now, almost 5-6 years later, we see actually generations of new ARM, Apple SoC coming up. There are different CPU design, GPU designs, a new introduction of the NPU, neural processing unit, and all the like advanced matrix operation to think about different ML capabilities. And things also got bigger, right? There are different size of SoC from like things like in your AirPods, all the ways to things like in your desktop and also big iPads, right? So things has changed a lot, and things also have matured a lot, thinking about building bigger and also more complex SoC from different vendors. And it's not only just for Apple, right? You actually think about NVIDIA, and it's really hard to define what GPU even is these days, right? We talk about GPU, like for Blackwell generation, it's already triplet, right? We're talking about different triplets actually integrated together, will be further specialized even to have IO triplet and compute triplet, and even more triplets will be integrated. And that's only on the GPU side, right? For folks are really thinking about different SoC integration or system integration, and we're seeing different opportunities for different vendors to setting up their own IP portfolio, right? Even for vendors like NVIDIA, it's not the only GPU, like or CPU portfolio, their DPU portfolio, right? We see a range of different hardware being designed to meet this demand. And here we're only talking about compute, right? And then there's a whole entire layer of how the different compute chip actually being connected together. We're talking about scaling up network, scaling out network. And when we think about compute unit, right, people today are talking about racks of compute, right? How they are connected together, how we work together, how they actually architect gigawatts data center to connect all the different components together, right? This is a really exciting time where people are building really complex things, and the scale has really not been actually explored much in the past, and that actually lead to a lot of interesting problems. Think about how we actually go generation by generation, right? So every generation we like to advance our compute, what kind of features we like to bring in. Ben mentioned that there is already, we see like limitation of technology scaling. How do we actually build better hardware platform? Where is the source of improvement, both at the chip level, but also at the system level, at the interconnect level? This is really exciting time to think about the complexity and also the powerfulness of how powerful today's hardware and also future hardware is gonna be. So that's on the, I guess, traditional, typical semiconductor companies these days, right? But also moving forward, another part really important is that some of you maybe also start doing like job search, career fairs, right? And I've got like a lot of people talking about how to navigate the job search process. But today, when we think about the hardware design, it's not only just the traditional like CPU companies, GPU companies, SoC companies. We see a range of actually new player actually in the hardware space. Google has been actually successfully deploying generation of their tensor processing unit for machine learning applications. It started with actually serving their internal needs, and more recently, you have already seen a lot of news about actually other players, other users are actually using Apple's TPU as actually the way they actually train their big models, right? So now Google is also in some sense a hardware supplier, right? They're building their hardware, they're supplying their hardware to actually different frontier labs so that people can actually train large models. So with that, it's also really important to think about how different, especially system or even software company can actually participate in the hardware industry and what are the benefits and the pros and cons in navigating this kind of very complex space. So that's, I guess, different components thinking about the industry. I want to go through some of the courses. We did multiple iterations of that during the advising session and also during the office hours. Many of you are very familiar, probably very familiar with, like our course roadmap. Here is where we are, X151 to 51A, talking about digital design and also hardware circuit. But moving from 151, you can do actually a lot of things. It unlocks actually a lot of courses you want to take, and I may be very interested. I will go through a couple of them. There, in particular, some new courses I think will be actually very important, and also happy to have later conversation about the different components. With this, I think several of you actually have already taken 151 and 251A. This is our computer architecture class. This class can be taken with 151 in any order. For folks, if you haven't taken 152 yet, take it in the spring. I heard the enrollment is also pretty high. And it's actually a good experience. Now you understand how you can build things, and you're very confident about you can actually produce a CPU with a particular spec. And now 152 will talk about more advanced architecture features. What are more than CPU actually look like? What are the modern accelerator and the GPU look like? How you can actually material some of the designs using the skill set you already learned in 151 to think about how you can actually design and architect some of them. So a great class. If you're interested in computer architecture, almost a must take, right? This is also one of my favorite class when I was a student. If you're really interested in the circuit side, like I mentioned, we only touch some of the surface of the circuit component, and there are a lot more exciting components that you can actually learn in our course curriculum. Then I would strongly recommend you to take 251B. This will also be offered in the spring, and we're in the process of actually finalizing the TAs and also different component. You'll learn actually a lot more deeper component on the circuit concept. In particular, like memory is a really important part. Power and power management is also really, really important. We barely touches power, right? We have a very high level component thinking about the power, but we didn't really touch about how people actually optimize power in their circuit design, right? So again, a really cool class has been actually also enrollment has also been growing consistently in the past few years. So if you're interested on the hardware side, circuit design, this is also a great class to take. I strongly recommend it. Another one, this is a class I will be teaching, and this is also the class my first time will be my first time teaching this class. I'm really excited. I think many of you might already be enrolled in the class, so I'm really happy that we can actually go through this together. This is our tape out class. As the name suggests, we're going to tape out a fairly complex SoC, actually 2 chips, one digital and one analog, in the next semester. It will be a fun class. This is my first time teaching that. We have a great team of staff. We're in the process of preparing the materials. It will also be a new process technology. Many of you know that we have been using Intel for the past 3-4 iterations of class, but this is a year. Next semester, we'll be transitioning to TSMC. So we'll be learning a new process technology, see how it works, and we have a new design that will also currently being architected, and will also have all of you with your unique contribution, your way of thinking about hardware. We get to actually build something actually brand new that we haven't done that before. So this will be a really, really exciting opportunity. I'm really excited, but this is also a lot of unknown. I have taught a lot of classes here at Berkeley, but this is a class I've never taught. This will be a fun experience. I'm looking forward to working with all of you, especially for those, particular for those who have already enrolled in the class, to actually build something really amazing together. Together with that, there will also be a bring up class in the fall. I think this is also a really cool platform to actually thinking about the chip bring up process. I will talk a little bit more when we get to the tape out, but again, strongly recommend to go through the series so that you can actually get the full exposure of the chip design process. There's a new class or like an updated class. I also want to mention particularly, this is our introduction to design automation class. This is a class that we actually have already been working with the core staff for 144 in thinking about how we can better connect 151 designs, the designs that you already know, understand, the lab that you have been working on here, so that they can actually use this class to teach you the concept of the different, how the modern actually CAD tool works, what is verification. Anish gave like a really good overview about formal verification, and that class you actually get to execute different verification plans, thinking about coverage, mechanism, and the ways to actually make sure the design that you're building actually makes a functionality. So there will be a lot of new updates, and we make it make sure that it's actually the new updates is consistent with the material that you already learned in 151. So this would also be a great experience. So I think that's all on the course side. I also want to use this opportunity to get more folks involved into computer architecture research. Throughout the semester, many of you reach out to us and also other faculties about opportunities for architecture research. Some of you probably heard from me. I was like, oh, focusing on 151, this will take a lot of your time, which I hope it is true, right? But now we're wrapping up 151. Now I want to welcome all of you to actually reach out to us again if you are really excited about the material, interested in doing more, understanding more how to actually think about future architecture system, building actually fairly complex system together. Now we're looking forward to actually engage with all of you, think about the platform components that we can bring together. It will be fun. And in some sense, I think it will be actually lighter than 151, considering the load that you have already been experiencing here. Now you are very prepared, and now you have this opportunity to relax and think about open-ended questions. And again, we're looking forward to get more of you involved. For the remaining few minutes, I do want to leave some thoughts like on hardware design, as now you folks are all prepared to execute their design and also to navigate both your career, job market, and also ways to think about things. In particular, from a hardware design point of view, right? What do we want to be, right? What kind of designer do we want to be? What kind of engineer do we want to be? What kind of design do we want to design, right? I think that's probably some of the questions is on your mind, and it's also having on my mind throughout my career. At the end of this particular class, where you folks have navigated, I think, one of the most challenging components of the computing stack, I do want you to maybe just remind you, but also opportunity for you to think about how to grow moving forward. In particular, I do think for future computer architect or hardware designers, what's really important is to think about how you can grow. You already have an anchor point, right? Everything you learn from Berkeley, especially 61 series 16, get to your 261C 105, now 151. You already have an anchor point. You know a lot of things, but the modern system is also fairly complex, right? We talk about the entire stacks. There are so many components. There are applications, system layer, hardware there. We talk about circuit. There could even be device. There's like design automation. All of those are very interesting and also important principles. It is time to think about how to become a Renaissance person in the sense that you have your anchor point. There are things that you know extremely well and also very comfortable ways, but also brave to actually break all the abstraction. Think about how you can actually learn other components and what other component can enable you to do more things. Even for hardware design, right? We will talk about like specialized design, machine learning, all the different machine learning, how to actually implement it onto the hardware. It really involves like layers of abstraction, but also thinking about how you can do what people call hardware software co-design to actually bring different components together. And more recently, we see the power of machine learning. There's also a lot of opportunity, even from methodology point of view, to bring machine learning and using that as a mechanism to actually transform hardware design, right? All of those are really, really important. And all of you here at Berkeley have a really unique opportunity to learn from all the different components. Think about how you can actually build your own knowledge base, understand the complexity, and see how you can actually navigate across different layers. So it's really important to learn all the different layers, but also be willing to break abstractions and really start thinking about for vertically integrated ideas. Next, I'm going to talk about two components. In particular, what architecture really is, right? This is not specifically for architecture as like the definition of architecture, which particular layer we are at, but more is like what's your mental model in your future career as an engineer, as a designer, as an architect. How you think about the architecture that you will be designing, that you will actually be leading. I want to leave you with two thoughts. One is, in some sense, architecture is a reflection of time. We talk about, in particular, especially in 61C and 152, we'll talk a little bit more, but architecture is really the layer, even the broader system, right? Is a layer that really connecting application and technology together. And one thing you will know, and you have already been observing, that application keep changing, technology also keep changing, right? Nothing is always there, which basically means that you need to be, or we as a designer, as an architect, need to be adaptive and also evolve with the demand of the application and also the underlying technology. See what has changed, what has been not, and think about how you can build the architecture that really reflects your time, right? What is the what is the current requirement? What kind of compute platform we actually need, and how that can be maybe even mingled with the computer architecture principles that have you learned here at school. In some sense, part of the Berkeley education is a very important experience, right? Where you learn principles, you learn key innovation in the past, but they should not be the burden for your future exploration. Think about what are the future requirements. I don't even know, right? You have a very long 40, 50 years of career. You may actually run into different technology. There might be another different flavor of application, right? So here we want to give you like things that I guess we learned in the past, even the people before us learned in the past. But moving forward for your career, you will run into your challenges, you will run into your demand, you will run into your application or technology, right? You don't have to just do what have happened in the past. Think about what you want to do, what you want to build moving forward. It is build some hardware, yeah, in particular, be brave, build hardware that reflects your time. During my PhD, I read this a lot, this particular sentence. A new scientific truth does not triumph by convincing its opponents and making them see the light, but rather because its opponents eventually die and a new generation grows up that is familiar with it, right? You folks are the new generation, right? You folks carry your own thought. You folks may have your own technology advances and also challenges. Now it's really important to think about what kind of architecture you actually want to build. Another thought I want to leave here, I guess we have a couple minutes left, also related to architecture. We'll talk about how things have been adaptive or things have transformed in terms of over time. But in especially more recently, right, architecture is also really a conversation about space. What do I mean by that? If I think about more like the traditional architecture, especially the architecture that I was actually personally trained with, right? When I learned computer architecture, it's all about CPU, auto order execution, all the like scheduling mechanism, branch prediction, all those mechanisms. In some sense, it's almost feel like skyscraper, right? So we want to actually build something fairly complex that can actually execute a lot of things really, really fast in high throughput. Let's think about all the fancy mechanism that we can put together to actually build a skyscraper. even these days, right? In some things, if you look at today's GPU, TPU, like all those like emerging platform in thinking about how we execute, how we think about parallelism or locality, it's more spatially distributed. It's almost like for folks who have been to China or Beijing, it's almost feel like hutong in some sense, right? It's like each of the houses is like not too big, right? It's like very basic, but you get to need to actually connect a lot of them, right? They're very complex, like channels between them. You need to interact with your neighbor. Think about how computation is actually mapped onto different components, right? So with this, I do want to think about when you design your hardware, right? Be considerate. Understand your neighbors and also understand yourself, right? Your hardware, your piece of hardware will likely not be the only hardware exist in the compute ecosystem. It will be one of them, and they need to be interacted and connected together, right? So know your enemy and know yourself. That's the secret to success. So with that, that's the thought I want to leave you about architecture. Again, those are my view, but I do hope you actually explore different components and think about how you want to design the architecture that you like as part of your career. As a final thought, I do want to thank all the amazing staff that I have and we have this semester. This is a really fun year. I haven't taught this class for almost a year and a half, so actually I didn't know most of the staff. So this is also my opportunity to get to know them and also get to work with them. They put in a lot of effort into the class. Sometimes I saw like 2 a.m., 3 a.m. posts from Slack, like all the ads, like look at the ad stats, like everyone is trying to on there helping you. And this is also a learning experience for our teaching staff, get to work with students, think about how to articulate ideas and interact with them. So they're really, really amazing. And I hope you folks get to opportunity to interact and work with them. In particular, I like to thank Professor Keller joining me this semester. Ben has been really good coworker and a very good friend. And when I know I need to actually teach this class in a particular hour, that will be very, very challenging for me. I'm very grateful. Ben actually, well, I reach out to Ben and Ben is willing to help. I know Ben is going to be great. I work with him. He knows everything. He's very articulate. But Ben is just amazing. He's a really good teacher. I didn't know, but he's so good. I learned so much about teaching from him, and he actually cared about things. He joined all our meetings, brainstorm things, and interact with the students. I hope you folks also have a good experience interacting with Ben, and I hope we get to keep Ben for as long as possible, and looking forward to teaching more classes with Ben. With that, a final note, thank you to all of you. I mentioned I haven't taught this class for a while, so I'm really excited to get to know all of you through this semester. It has been really, really amazing. I personally, I had a lot of fun. I hope Ben also had a lot of fun. I hope you also had. I'm very happy to see many of you here. Maybe as the final note, at the beginning of the semester, I mentioned folks in the semiconductor industry is always optimistic, right? The entire area is very weird. We have this kind of weird law just predicting the end of everything, things not gonna work. And years after years, people are pushing forward and thinking about new technology and the new mechanism, right? Stay curious, stay optimistic. This is an exciting time for the industry, and you folks are very well equipped with amazing skill set and also ways of creativity to think about future things that you can do. This is really, really fun field. I hope we can stay connected and looking forward to interact with all of you. So good to see you. This is the end of the lecture, but not the end of the class. We'll see you next week for the project checkoff. Everyone needs to sign up a slot and show up. And we'll see you the week after for the final exam. Good to see all of you. Thank you, everyone. I hope you had a great semester. This is the end of the lecture. Thank you. What's that? What's that? Oh, thank you. This is really fun. Great.
We're gonna do it.
Yeah.
Great job.
Yeah.